Swayam Prabha. Digital India. Educated India.
Hello students, in this lecture I will be teaching you various synthesis methods for nanomaterials. So there are various methods to synthesize nanomaterials. There can be top-down approach, bottom-up approach and chemical, physical and biological synthesis approaches. Okay. So top-down, which is mostly physical, and bottom-up, that is mostly chemical and biological. So let's study these in detail. Why does it matter that what method we are using to synthesize? Okay, so basically the properties of nanomaterials depend completely on the method that you are using to synthesize them. If you are using bottom up approach or top down approach, the properties can be completely different. Nanomaterials can be of different sizes depending, different shapes and sizes depending on what method you are using to synthesize. So the same nanoparticle that you are using to synthesize, you can use the bottom up approach as well as the top down approach. And for some materials, the top down approach is better, for some bottom up approach is better. So let's study these in detail. And choosing the method also determines the function and applications of these nanomaterials. So choosing the right method also determines the cost and scalability of the material. So like if you want things to be cost effective, so you are going to choose a particular method, or if you want a particular material on a particular scale, then you use a specific method for that. So, and it is very critical for nanobiotechnology and biomedical use. So methods are very important, whatever method you are choosing. So what is top-down approach? So when you break down something from bulk to nanoscale, that is top down. Like when you want to approach, when you want to create something of a particular size, there are two ways in which you can make that. You can break down, imagine if you want to create something on a particular scale like a nanoscale, okay. So you are either breaking down a bulk material into small parts and to that scale, or you are building up from a smaller scale to that scale. So it's like that. On a scale, you're going from bulk to small size, or from small to that particular size. So that is what is meant by top down and bottom up approaches. So top down approach is basically bulk to nanoscale, and bottom up approach means atoms or molecules are making a cluster to make nanostructures. They are coming together to form nanostructures, okay. Both approaches are complementary, and selection also depends on the application and scale. You can also use both methods. Hybrid techniques are also available. So that is the top-down approach, where this bulk material is being broken down into smaller parts in powder form. Nanoparticles are formed. Or bottom-up approach, where small atoms, they are forming clusters to form nanoparticles. So that's the basic difference between top down and bottom up approaches. Now top down methods include several techniques like ball milling, lithography or etching, that is from bulk material to nanoparticles. So these are the methods that we use. These are mostly physical methods where you are creating material from bulk to smaller sizes, like ball milling, lithography and etching. I will be explaining these in detail in my next slides. Then these can be bottom up methods, sol gel process, chemical reduction or hydrothermal. So these are from atoms or molecules to nanoparticles. Remember, the size of the atoms and molecules are like in the atoms and molecules are very small size, and when they come together they form nanoparticles. This is how bottom up methods go. Then physical methods include laser ablation or evaporation condensation. These are very high energy techniques. They will require high energy to create that. So it depends on your requirement, on what you are trying to make and how much resources you have. And Then there are biological and green methods. They may be plant mediated or microbial synthesis. And these are eco-friendly synthesis. So if you want to make something biocompatible or something like that or eco-friendly, so you are choosing this method. So you can see top down methods are mostly physical method, bottom up methods are mostly either chemical or biological. So let's revise this, because this will matter as you create more, as you study more approaches, more methods of synthesis. This will, you need to have a clear idea of what this is. So top down approach, basically top to down, this is what it means. Starts from bulk material and reduces size. It relies on mostly on physical and mechanical processes. It has limited control over surface defects. Okay. So when you're breaking something down, you know that things can be defective. You cannot prevent, you cannot control surface defects. So the material that you will be creating will have a lot of surface defects. Then it is suitable for large scale fabrication. You want to create something on a larger scale, then you use the top down approach. So these are some top down approaches. Mechanical milling, where a basic material is grinded, coarsely grinded into smaller particles. So it is first it is coarsely grinded, then it is fine grinded into very small nanoparticles. So that is known as mechanical milling. Then it can be nanolithography. What does lithography mean? Litho means stone, graphy means writing. So we are writing something on a solid material. So that's the sample, and an electron beam is put down to create a desired material. Then there is thermal decomposition. As you can see, an entire zinc complex upon thermal composition and zinc oxide nanoparticles are formed. So this is via thermal decomposition. Then there can be laser ablation, where a high intensity laser beam is put down to cut down particles, bigger particles into smaller nanoparticles. So that is laser ablation. Or there may be sputtering. So what does sputtering mean? Some high energy gas is put down like argon, and it is put onto some substrate material and atoms are sputtered out of it. Okay, the materials are deposited over here, nanoparticles, and they grow here. That's ball milling in detail. What is ball milling? It's a very commonly used method. So this is the direction of the mill. It's like it's rotating. So imagine a ball that is, you just put a ball and roll down on a floor. It's like that. This is a mill that is rotating, and you put in it some grinding material and your nanomaterials. So that grinding material is going to, as the ball rolls down, the grinding material is going to grind that nanomaterials that you put down. So it's like you consider all this in a ball, and you have these as grinding material, and you have these particles coming in between. So this goes like this, and the material is grinded into fine particles. So this is grinded into fine particles as it comes in between this. So that is how it works. Then there is lithography, where a photoresist material is used. Photoresist are basically polymers that are used. These are highly photosensitive polymers that are used, and then you put a mask on it that has some pattern on it. So you are putting a mask on it that has some pattern. You're putting it on a these might be of silicone, these patterned masks, and these are put on the photoresist, and you are putting that under UV exposure. So UV lights comes like this, and this is your patterned mask, and this is your photoresist on a semiconductor layer. So what happens is that upon UV exposure, the resist develops. You put some pattern, that pattern comes over on this, and then you put this in a developer solution. So as you put this in a developer solution, the softer thing that washes away. So the softer comes into it. Okay. So if the resist is soft, then that part comes into the solution, and if the resist is harder, then the surrounding material goes into that. So these are etching ions, and that is how quantum dots are created from lithography. And then there is etching, like KOH wet etching, you can see. So etching, as the name suggests, basically etches the material into it just creates etching, basically it etches a material. So these are suspended structures, these are 3D structures, and these are hybrid structures. So silicon micro nanostructures are created like this on this silicon strip. So basically you are etching, making spaces on a material and then filling it with your desired nanoparticle. These can create either suspended structures or 3D structures or hybrid structures. So we have studied top-down synthesis techniques. These may be mechanical milling and attration, or lithography, which can be photolithography or electron beam lithography. Then laser ablation, where a high intensity laser beam is cutting your materials into very fine nanoparticles, or etching and machining methods, where you are etching something, you are creating space for your nanoparticles, and then you are dipping that in your nanoparticle solution and creating something on that. So what you have learned so far, the top-down synthesis of nanomaterials. So when you need to break down bulk materials into nanoscale structures, you use the top-down technique. Here you have a control over the size and shape. So this is very important. Why you are using this technique is because we want to have a control over the size and shape, or then you use top-down nanomaterial technique, the top-down synthesis for nanomaterials. And the advantages may be that it is simple and cost effective. You are just using an instrument and you are breaking it down. So it is simple, cost effective, we can say, not much, because you are using a high energy setup to create that. Then purity is high because you are not using any other chemical in that or any other biological thing in that. So you are just breaking down a bulk material into smaller particles. So the purity may be high, that you do not have chances that you do not have that much contaminants in your final product. Then the scalable production. If you want to create something on a bigger scale, you want to create a large number of nanoparticles. So this is the apt technique for that, the top-down synthesis. And you can create nanoparticles, nanowires, quantum dots or nanoplates out of it. So what are the advantages of this method? Advantages is that it is scalable and of industrial relevance. So you want to create something on a large scale for an industrial purpose, then you go to choose the top-down approach. Comparable with microelectronics fabrication, then limitation, and also if you want something of higher purity, then you go for top-down approaches. Then limitations is that there may be surface damage and surface defects. So obviously when you are breaking down something on a physical level, then chances are that there can be surface damage and surface defects. So this can be a limitation. So if you want to use something precisely, then this might not be a very good idea. And this limited atomic level precision. So obviously when you are breaking things down, so atomic level precision can be a little less. So what is bottom-up approach? Bottom-up approach is basically where you are building something from atoms or molecules. So you are building something from a small, like you are building something brick by brick. You are building some building out of small bricks. It's like that. So you are making nanoparticles from smaller atoms or molecules. That is bottom-up approach. So you are going from bottom to up on a scale. So this relies mostly on chemical and biological interactions. So how do you combine something smaller into bigger? You use chemical and biological interactions to do that. Some bonds will be formed or some interactions will be made so that these smaller materials come together to form a particular nanoscale size material. So here there is high control over size and morphology. So you have a precise high control over size and morphology. Whatever size you want to create, you can choose that, and morphology also you can control. Then it is inspired by natural self-assembly processes. So as like phospholipids in water, you can see they naturally self-assemble. So it is inspired by that natural process. So in nature also things are self-assembling. So inspired by that, you can use the bottom-up approach where self-assembly process is used. So atoms and molecules self-assemble into nanomaterial, nanoparticle. So let's revise what a bottom-up synthesis of nanoparticles was. So you either use chemical reaction, self-assembly or something to create a nanomaterial. So that just for depiction purpose. And so when you're building up nanomaterials from atoms and molecules, you use the bottom-up synthesis of nanomaterials. So here you have precise control over composition. So whatever composition you want, you can create that with this. So advantage is that there is high uniformity, like you want to obtain uniform sizes. Like if we were using top-down approach, then if you're breaking something down, you do not control every the size the size and shape of every particle, right? So imagine you're breaking something, so forget nanoscale for a moment, imagine you're breaking something with a brick. So you cannot create uniform sized particles. So here when you're building up from scratch, like you're building up from atoms or molecules, then the uniformity may be high. You can create uniform sized and uniform sizes and shapes for the your material, okay. So you can create wide range of materials from this. You can take the same material and create a wider range of materials. And if you want to create complex structures, then also you use this method, because if you want to create complex structures, you need a certain uniformity, you need a certain precision that is possible with the bottom-up synthesis. So you create nanoparticles, nanotubes, quantum dots or nanorods according to your requirement. So these are the chemical synthesis techniques. You can use sol gel method, chemical reduction of metal salts, or hydrothermal and solvothermal synthesis, or chemical vapor deposition. These we will be discussing in detail in our next slide. So these can be either, this is chemical synthesis method, okay. Sol gel method, chemical reduction of metal salts, hydrothermal and solvothermal synthesis, chemical vapor deposition. So let's start with the hydrothermal method. So in this method you are using a sample extract. Sample extract, like whatever extract you are using to obtain your nanoparticles. It can be biological, it can be a plant extract. So imagine that you're making a plant extract, so you're taking or you're using a dried potato peel, you put it in water. So that's your sample extract. So you have your sample extract in this, and you have your sample extract in this, and you heat that on high temperature for a long duration, like for 18 hours. So you're heating it on a very high temperature, like 220 degrees Celsius, and for 18 hours. So that creates this liquor, okay. Now you add new distilled water to it, and you rotate that for 10,000 to 20,000 rpm on 10 to 20,000 rpm and centrifuge that. So you obtain your nanoparticles, your desired nanoparticles. So what did you do? You took the sample extract, you heated it to around 220 degrees Celsius for 18 hours. Then you obtained this liquor, and then you drained that liquor out, added new DI water, then you rotated it, centrifuged it you rotated it at 10 to 20,000 rpm, and you obtained your desired nanoparticles in the centrifuge. So that's your sol gel method. Here you are using precursors with solvent. So you have your solvent and you have your precursor over here. From precursor, whatever nanomaterial you want to obtain, you have a precursor for that. So you put your precursor into the solvent, and a colloidal structure is formed in sol, and then there's connected porous structure, and then the supercritical drying, thermal drying and freeze drying. So you're drying this sol solution, you're drying this the supercritical drying or thermal drying or freeze drying. You're drying this into aerogel, zerogel or cryogel. So you're drying, basically you are starting with the solvent, you are drying it to obtain aerogel, xerogel or cryogel. So this is the outcome. You obtain your nanoparticles in powder form. So this is the chemical reduction method. It's a very widely used method. You can easily obtain that. You can also synthesize that in your lab if you want to. So you start with a metallic salt solution. This is mostly used for metallic nanoparticles. So if you want to make a gold or silver nanoparticle, that I'll be discussing in my next slides. So if you want to create some metallic nanoparticle, you start with that particular metallic salt solution. So you heat that salt solution to ionize the salt, then you put the reducing agent into it, and then metallic salt solution is basically reduced, and then you put a capping agent. Capping agent is mostly certain polymers that surround that your particles to give them stability so that they don't stick together due to electrostatic forces. So now you have your stabilized metallic nanoparticles in your solution. So you have a solution of your desired metallic nanoparticles. Okay. So what did you do? The metallic salt that was required, whatever nanomaterial you wanted that was desired, you started with the metallic salt, the same metallic salt solution, and you heated it. Then you added a reducing agent. Then you heated it and you added a reducing agent. Then you added a capping agent, and then you obtained your desired metallic nanoparticles. So that's chemical reduction method. Then there may be chemical vapor deposition method. So here you have a quartz tube, and that is where you put your sample and you pass a gas through it, and there is a catalytic decomposition over here on high heating, and you put this in oven. Okay. So that is chemical vapor deposition method. So it is deposited over here. So that's a comparative summary table. These are your methods that you've been using. The sol gel method, product type that is obtained is mostly oxide nanoparticles or films, and you have a high control over your over what you want to synthesize. The properties on the particles that you synthesize, you have a high control over that if you are using the sol gel method. Low to moderate temperature is required for this, and typical materials that are synthesized by the sol gel method is silicon dioxide or tellurium dioxide. Then chemical reduction method. So the product type is mostly metal nanoparticles. We use this in lab. If you want to create metallic nanoparticles, we usually use this method, the chemical reduction method. So control is moderate to high. You want to control precisely whatever you are creating. So control level in this method is high. You can control that. You can control synthesis and properties of the materials that you are synthesizing with chemical reduction. Then the temperature used is low, not exactly low you are heating that, but low means comparatively low, because we are dealing with very high temperatures also in thermal methods and in physical methods. So compared to that, low temperature is required. Then typical materials are silver and gold nanoparticles, that I will be discussing in detail. So there can be hydrothermal method, which is used to synthesize crystalline nanoparticles. So we use this for creating carbon dots. So control is high. You have a precise control over what you are synthesizing. Temperature used is moderate as compared to other methods. And typical materials are zinc oxide or iron oxide. So you want to create iron oxide nanoparticles, you are using hydrothermal methods. You want to create carbon dots, you are also using hydrothermal methods. So these are the methods. Then there can be chemical vapor deposition, which is mostly used to create films and wires. So you are depositing something on a surface, so you can create films and wires easily. Control is very high, so you can precisely create what you want to create. Then temperature is high. High temperature is required in chemical vapor deposition, and typical materials that are synthesized are carbon nanotubes and graphene. Nucleation and nanoparticle synthesis. So nucleation is a process whereby nuclei acts as templates for crystal growth. So nuclei, basically these are like seeds. Nucleation can be defined as a process, initial process in a crystal formation from a solution liquid or vapor, where a small number of ions, atoms or molecules arranged into a characteristic pattern of a crystalline solid, creating a site for further particle deposition as the crystal grows. So that's the definition. So what is nucleation? It is a process after you put your precursor. What happens is, how do nanoparticles form? They just don't form just like that. First nucleation happens where the tiny seeds are formed that act as templates for crystal growth. So it's like the initial process in a crystal formation, like crystal is being made and there's this initial process where a small number of ions, atoms or molecules, they arrange into some characteristic pattern, and then on top of this pattern, basically it acts as a site, like on top of this pattern further particle deposition starts happening. So it's like a seed. At first the seed is formed and then on top of it particles start depositing, and it forms a full grown crystal. So as you can see in the figure, precursors are being used and they can be fast nucleation or they can be slow nucleation. On fast nucleation, growth happens into smaller nanoparticles. On slow nucleation, growth happens into larger nanoparticles. So you are using a precursor, you are reducing, basically remember that how you were creating your nanoparticle, you were reducing your solution and then you obtain some precursors, and it's like you obtain some seed and you obtain some precursors, and then upon fast nucleation you form these seeds. These will act as templates, and upon these particles atoms and ions will grow and your nanoparticles will be formed. And when it is fast nucleation, small nanoparticles will be formed, and upon slow nucleation growth will happen and large nanoparticles will be formed. These are the common synthesis methods of gold nanoparticles. So I will be giving you two examples of chemical synthesis of metallic nanoparticles. Two of the most commonly synthesized nanoparticles, gold nanoparticles and silver nanoparticles. So that is the Turkwich method or citrate reduction method. So you heat a tetrachloroauric acid solution and add sodium citrate for reduction. Sodium citrate acts as a reducing agent. So citrate is reducing gold ions to zero valent gold. Zero valent gold, it is citrate is reducing gold ions to a zero valent gold and stabilizing them, causing a color change from gold to red. So you see how gold is changing into red color. Like I've already told you how gold nanoparticles change their color. So you're creating your initial precursor is basically tetrachloroauric acid, and you're starting the solution and adding a reducing agent, that is sodium citrate. So sodium citrate is reducing your gold ions to zero valent gold and stabilizing them, causing a color change from gold to red. You can control your synthesis of gold nanoparticles. You can control their shape and size by changing the gold to citrate ratio, and this forms a creates a precise control for the particle size, that is 10 to 20 nanometer. Then there can be chemical reduction method where stronger agents of reduction are used. So you're using strong reducing agents like sodium borohydrate with chloroauric acid and citrate, that is often leading to smaller differently shaped particles. So you want to create smaller particles, smaller gold nanoparticles, and of different shapes and sizes, you use other chemicals, other reducing agents. So you see how precisely you can control the shape and size and color of the gold nanoparticles using the same precursor solution, that is chloroauric acid. So you are starting with a gold metal solution, you are starting with a gold metal solution and then you are reducing it with sodium citrate, and you are achieving a zero valent gold, and the nucleation happens and then growth on those nuclei happens and these coalesce and then cleave to form gold nanoparticles, and it is capped with a polymer for its stabilization. That is how gold nanoparticles are created. Then synthesis of silver nanoparticles. The chemical methods, most commonly used chemical methods, the chemical method is the most commonly used for the synthesis of silver nanoparticles. We reduce a silver salt over here. Similarly, as similar to the gold nanoparticles, we are using a silver salt as a precursor, that is silver nitrate. It is reduced to metallic silver using a reducing agent, sodium borohydrate, sodium citrate, ascorbic acid, tolerance reagent or polyols or DMF. We are using these agents as reducing agents for the reduction of the silver salt and the silver salt is again reduced to metallic silver, a zero valent silver, like a zero valent gold that was reduced in the when we were synthesizing gold nanoparticles. So then we use stabilizing or capping agents to prevent agglomeration. These capping agents are polymers that can be like PVP. These can be polymers that are used as capping agents. So we can use PF or PVP. Then example is mixing silver nitrate with NaBH4 and capping agents under controlled conditions. You mix silver nitrate with NaBH4 and use certain capping reagents under controlled condition, that creates your silver nanoparticle. So that's a crude picture. We are putting an aqueous solution, putting a reducing agent, silver metals, a silver metal solution, and reduction is happening over here, and at first nuclei will be obtained, and then on that nuclei deposition will be formed, and you will obtain your, and then you put a capping reagent, and then you will be obtaining your silver nanoparticle formation, and you will be obtaining your silver nanoparticles as desired. Then this physical synthesis techniques. Physical methods can be physical vapor deposition, thermal evaporation, sputtering, or arc discharge method. So these are the physical synthesis techniques: physical vapor deposition (PVD), thermal evaporation, sputtering, or arc discharge method. So thermal evaporation, what you are doing in thermal evaporation is that you are evaporating a material by heating it in a vacuum chamber to directly deposit vapors onto a cooler substrate. You are heating something at a very high temperature and you are depositing it on a cooler substrate. So this is what it looks like. This is an animated picture actually. Thermal evaporation is this is just for depiction purpose. The thermal evaporation is basically evaporation of a material by heating it in a high vacuum to directly deposit vapors onto a cooler substrate. Or it can be sputtering, that is bombarding of a target material with energetic ions to eject atoms which deposit onto a substrate. So basically you are using some highly energetic ions like argon to eject atoms which deposit onto a substrate. So you have your material, you are bombarding it with, you have a target material, you are bombarding it with energetic ions to eject atoms which deposit onto a surface, that is known as sputtering. Arc discharge method, where evaporation of a rod shaped target through a high current arc discharge produces nanoparticles from the plasma. So here is a high current arc discharge, you are putting a very high current 50 to 100 amperes from an arc, and you are putting your material over here, and it evaporates instantly and deposits your nanoparticles, and it produces your nanoparticles from the plasma. So examples and advantages. Advantages is that thermal evaporation is basically simple and fast method. Examples are that silver, gold and metallic ozone nanofilms are made from thermal evaporation, and advantages of sputtering is that high adhesion and good purity, and examples are silver and nano, these are basically metal oxide nanofilms. With arc discharge method, you are creating carbon nanotubes and fullerenes, and advantages is that it is of high purity, it is simple and fast. Then there is biological synthesis techniques. So what is biological synthesis technique? You are using microorganisms, plants or enzymes to create your nanomaterials. So you are using these as your substrate to create, basically not substrate, but you have, I will be explaining this in detail. These can be used as reducing agents, or it can also be used as a starting material. So basically biological synthesis techniques are where you are involving something biological like microorganisms, enzymes or plant extracts to create your nanoparticles. So if you want to have a eco-friendly approach and a sustainable approach, then you are using biological synthesis techniques. Although when you are using biological methods, so you cannot create something in bulk, so it will require like if you want to synthesize something lesser amount, then you are using biological synthesis technique, but you can be precise over here, you can be eco-friendly and sustainable. These can be biocompatible materials can be synthesized from these biological synthesis techniques. So it produces biocompatible nanomaterials and it is strongly relevant to nanobiotechnology. So that's biological synthesis. of nanomaterials. So you start with biological extracts. These may be plant extracts, or these may contain microorganisms. So whatever it is, you are starting with something biological over here, biological extracts, plus metal solution. The metal that you want to have, like metallic nanoparticles, whatever that you are desiring, it is over here in the metal solution. You want silver nanoparticles, it is some silver solution, it is the silver salt solution, or it's a gold salt solution. Whatever you want to synthesize, it is over here in the metal solution. These are biological extracts. So that's biological extract plus metal solution. Then on some particular pH, temperature and pressure, on a particular pH, temperature and pressure, reaction happens between these two, biological extracts and metal solution, reduction reaction happens. So nanomaterials are basically formed upon reducing this metal solution. So metal solution is reduced to form this solution, and then you put a capping reagent into it for stabilization. The capping reagents are mostly polymers that you are using. So polymers you are using for stabilization of, so you basically obtain charged particles over here. They might just stick or agglomerate together. So we are using capping reagents to synthesize these. So now you obtain your synthesized green nanoparticle. So over here you basically, the function of the capping reagent is to stabilize your nanoparticles. So now you obtain your stable synthesized green nanoparticle. Green nanoparticle means basically something that you have obtained from biological extract. It has nothing to do with green color. So that's a picture in detail. You have your metal salts. So how do you obtain your nanomaterials from microorganisms? So you have your metal salts over here, whatever metal nanoparticle is desired, silver salt solution or a gold salt solution, you have it over here. Then you put microorganisms, and there is a biological reduction from the enzyme secreted by these, or you took metal salts, you put microorganisms, and you obtained biological reduction of the metal salts. So you have reduced your metal salt via biological aid, and nucleation happens. Nucleation I will be teaching you in detail basically. So nucleation is happening, meaning your crystal formation has started over here, and then you put some capping reagent, and you obtain stabilized nanoparticles. And sometimes capping reagent is also present in microorganisms or plant extracts, so you do not have to use that from chemicals. Plant extract, if you obtain something from plant extract, it is like plant extract plus metal ionic salt solution, and there is biological reduction, nucleation happens, then accumulation happens, and you obtain stabilized and capped nanoparticles over here. And some controlling factors are taken into account, like pH, concentration, reaction time and reaction temperature. So it also depends on that, some factors, and you obtain your desired nanoparticle. So the blue part, that is the metal particle, red is the capping agent. These are the basically red, and this purple, and yes, this is the capping agents. So you can see the metal particles are all scattered when nucleation is happening. Biological reduction has started, and metal particles are basically scattered with capping reagents, and then they get clustered, accumulated, and your capping reagent is basically surrounding your nanoparticle, and these stabilized nanoparticles are obtained. Examples of biological synthesis, nanomaterial synthesis. Gold and silver nanoparticles can be synthesized from biological nanoparticle synthesis. These may be obtained by using bacteria or fungi. Then there can be DNA directed assembly of nanostructures. Or protein templated nanoparticle growth. You grow nanoparticles on a protein template, or there can be virus based nanomaterial fabrication. So there are many methods of biological synthesis that you can be using. So there can be many biological sources that you can use to synthesize your desired nanoparticle. So you can be using microorganisms, enzymes or plant extracts. So in microorganisms you can use bacteria. What is the mechanism that they provide? So they release enzymes, that is reductases, that reduce metal ions extracellularly or intracellularly. So bacteria basically release certain enzymes that can help in the reduction of your nanoparticle metal solution, whatever metal solution you are meaning whatever precursor metal solution that you are using to create a desired nanoparticle, you can reduce that metal solution using bacteria. So you were using your reducing agent earlier, now you can use bacteria as that reducing agent, as it is secreting certain enzymes like reductases which can reduce metal ions intracellularly or extracellularly. Examples are silver, gold or iron oxide nanoparticles. So you want to synthesize these nanoparticles, you start with the precursor metal salt solution, you reduce that with bacterial enzyme and you put a capping reagent and you form your desired nanoparticle. Then you can start with fungi also, where a high metal tolerance and secretion of larger amounts of proteins enable efficient reduction. So it secretes larger amount of proteins that enable efficient reduction. So gold and silver nanoparticles can be obtained from this method also. So depending on whatever your requirement is. Then you can start off with algae also, where polysaccharides and pigments act as reducing and stabilizing agent. So they can be acting as stabilizing agents also. So polysaccharides and pigments basically act as reducing and stabilizing agents. Stabilizing agents are nothing but basically they are polymers that cover your nanoparticle, your charged particles basically, they cover that and stabilize that and prevent them from sticking. So these can be naturally obtained from certain algae. So the polysaccharides and pigments that we obtain from these algae can act as reducing and as well as stabilizing agents. So here also you can synthesize gold and zinc oxide nanoparticles. Then you can use plant extracts. Plant extracts can have phytochemicals, flavonoids, terpenoids and phenols that act as natural reducers and capping agents. So here also you are obtaining your reducers as well as capping agents from plant. So what is happening in using plant method is that you get your reducing agent as well as capping agent naturally from certain substances that are present in plants. So or whatever organism that you are using, you can be using microorganisms or plant extracts and you get your reducing agent and capping agent naturally from that solution. So these act as natural reducers and capping agents. So all these nanoparticles you can extract this, you can synthesize these nanoparticles from plant extracts also. Silver nanoparticles, gold nanoparticles, copper nanoparticles or zinc oxide nanoparticles. Then isolated enzymes can also be used, although this can be expensive also because enzymes are, you obtain enzymes, enzymes can be difficult to obtain basically because they are difficult to maintain. They need a particular temperature and pH to work efficiently. They need a particular temperature and pH and it can be expensive and difficult to maintain, but these can directly catalyze reduction of metal ions. They can involve in the direct catalytic reduction of metal enzymes. So in isolated enzymes, this is also a biological source. This can be used in the direct catalytic reduction of metal ions. So nanomaterials that are obtained is metal nanoparticles with controlled size. So now you have obtained your nanoparticles with controlled size using all these biological sources: bacteria, fungi, algae. These are microorganisms, plant extract or isolated enzymes. So there are various application areas. These nanomaterials can be used in drug delivery, biosensing, as antimicrobial agents, in bioimaging, in cancer therapy, in tissue engineering. So depending on the application area, you can synthesize your nanomaterials. And what is the role of biologically synthesized nanomaterials in a particular application area? Basically for drug delivery, biocompatible carriers with enhanced targeting are required. So you need biocompatible carriers with enhanced targeting. So basically you create something from biological sources, you create biocompatible materials that can be highly precise in targeting whatever you are trying to target. So this is an advantage. Then in biosensing, In biosensing, as I've told you in my previous lectures, like enzyme and antibody functionalized nanoparticles can be created. So, you can use antibody antigen reactions for biosensing applications. So, you can functionalize your nanoparticles with antibodies. Antibodies are of the same nano material size, as I've already told you. You can functionalize nanoparticles with these antibodies. Okay. So, it's like you have your particle over here and you functionalize it with antibodies. That's surface functionalization. You put antibodies on the surface. Now it is highly specific to a particular antibody. So these can be your antigen. These antibodies can be specific for a particular antigen. So these can act as a sensing. These can be used for biosensing. This way, your enzyme and antibody reactions are used for biosensing applications. Then for making antimicrobial agents, silver nanoparticles are used for wound dressings. You already, you must be knowing your ointments for like burns and for wound healing gels and ointments, they contain silver nanoparticles. So, these can be used as antimicrobial agents also. For bioimaging, fluorescence and magnetic nanoparticles. So, nanomaterials can be used as natural fluorophores, and this can be exploited in bioimaging techniques. Then in cancer therapy, for targeted and controlled drug release, and for tissue engineering, scaffold reinforcement and cell interaction. So, cellular interaction can be used for tissue engineering purposes. So, these are the role of biologically synthesized nanomaterials, and these are the application areas where it is suitable. So, that is biological synthesis. And how many stars do we give for biological synthesis? For environmental safety, we give them 5 star. We give this technique a 5 star for environmental safety. For cost effectiveness, we give it a 4 star. For biocompatibility, we give it a 5 star. For size control, we give it a 3 star. There is not much size control, but it's like it's not very precise. Then for industrial scalability, we give it only 2 star. As you know, biological materials, you cannot obtain them on a higher scale, meaning you cannot obtain that in a huge amount that easily, and it is difficult to maintain also, because biological things, they exist on, they function on a particular temperature, they function on a particular pH. So, their functionality depends on particular environmental factors. So, industrial scalability is very less. You want to create something on a large scale for industrial purposes, you do not go for biological synthesis. And the relevance to nanobiotechnology, a 5 star, as we have discussed in the previous properties. It is very relevant for nanobiotechnology. So, the examples of biological nanomaterial synthesis: gold and silver nanoparticles using bacteria and fungi, DNA directed assembly of nanostructures, protein templated nanoparticle growth, or virus based nanomaterial fabrication. So, top down versus bottom up approaches. You compare the top down with bottom up approach. Top down approach is basically physical. So, that's let's just revise and differentiate between the two techniques. Top down approach basically requires physical size reduction. Bottom up is the chemical and biological assembly. Bottom up offers better atomic precision. So, you want to have a better atomic precision, you are starting from the bottom, and hybrid approaches are also increasingly used. You use both the approaches to create your nanoparticles. So, that is the short comparison of synthesis methods. The methods may be ball milling, the size control is poor, cost is low, scalability is high. You just want to create something on a larger scale, you use ball milling, but the size control is poor. As I have already told you, if you are crushing something randomly, you cannot obtain something of a particular size or of shape. So, it is not uniform also, and it is not very ideal for creating smaller size particles. Then the cost is low, although because you can the materials that you are required, the resources that you are using, they are not very expensive. So, the cost is low, scalability is very high, and purity is moderate. For sol gel method, the size control is good. Cost is moderate, scalability is moderate, purity is high. Then for chemical reduction method, size control is excellent, cost is low, scalability is high, purity is high. Then this CVD, chemical vapor deposition, the size control is excellent, cost is high, the setup is very expensive, the scalability and also the resources that are used are expensive, scalability is moderate, purity is very high. Then green synthesis methods, size control is moderate, cost is low, scalability is high and purity is high. So summarizing this, biomolecules can be used as tools for bottom up assembly. You are building something from down to up, then you can use biomolecules as tools for bottom up assembly. Then control of nanoscale architecture via chemistry. With chemicals you are using controlled nanoscale architecture. You are integrating biological and synthetic strategies. Then emphasis is on the structure controlled synthesis. So nanomaterials synthesized via top down and so nanomaterials can be, let's summarize this. Nanomaterials can be synthesized via top down and bottom up routes. Thank you for listening.
When I started creating this content for this particular course, Print Journalism in India, Traditions Meet Technology, that this would be beneficial for the students of undergraduation, researchers, academicians, industry experts, and those who have a keen interest in learning print journalism in India. Go to swayamprabha.gov.in, scroll it down and click on higher education or choice from there.
Hello and welcome to this piece of literary snippet. British humour doesn't have a very high standing in the world. When people talk about it, they usually do so with a certain degree of disparagement. Yet all this is, I think, rather unfortunate, because if I read out to you a certain section from Jerome K. Jerome's famous novel Three Men in a Boat, you will realize that not only is British humour genuinely funny, it is probably even better than some of the other samples of humorous writings that you might have read in the recent past. The story that I am going to read out is told by Jerome, who thinks he is suffering from some kind of a malady. I remember going to the British Museum one day to read up the treatment for some slight ailment of which I had a touch. Hay fever, I fancy it was. I got down the book and read all I came to read, and then, in an unthinking moment, I idly turned the leaves and began to indolently study diseases generally. I forgot which was the first distemper I plunged into, some fearful, devastating scourge, I know. And before I had glanced half down the list of premonitory symptoms, it was borne in upon me that I had fairly got it. I sat for a while, frozen with horror, and then in the listlessness of despair, I again turned over the pages. I came to typhoid fever, read the symptoms, discovered that I had typhoid fever. Must have had it for months without knowing it. Wondered what else I had got. Turned up St. Vitus's dance. Found, as I expected, that I had that too. Began to get interested in my case and determined to sift it to the bottom, and so started alphabetically. Read up ague and learnt that I was sickening from it, and that the acute stage would commence in about another fortnight. Bright's disease, I was relieved to find, I had only in a modified form. And so far as that was concerned, I might live for years. Cholera I had with severe complications, and diphtheria I seem to have been born with. I plodded conscientiously through the 26 letters, and the only malady I could conclude I had not got was housemaid's knee. I felt rather hurt about this at first. It seemed somehow to be a sort of slight. Why hadn't I got housemaid's knee? Why this invidious reservation? After a while, however, less grasping feelings prevailed. I reflected that I had every other known malady in the pharmacology, and I grew less selfish and determined to do without housemaid's knee. Gout, in its most malignant stage, it would appear, had seized me without my being aware of it. And zymosis. I had zymosis evidently from boyhood. There were no more diseases after zymosis, so I concluded there was nothing else the matter with me. I sat and pondered. I thought, what an interesting case I must be from a medical point of view. What an acquisition I should be to a class. Students would have no need to walk the hospitals if they had me. I was a hospital in myself. All they need to do would be to walk round me and after that take the diploma. Then I wondered how long I had to live. I tried to examine myself. I felt my pulse. I could not at first feel any pulse at all. Then all of a sudden it seemed to start off. I pulled out my watch and timed it. I made it 147 to a minute. I tried to feel my heart. I could not feel my heart. It had been beating, but now it had stopped beating. I have since been induced to come to the opinion that it must have been there all the time and must have been beating, but I cannot account for it. I patted myself all over my front, from what I call my waist up to my head, and I went a bit around each side and a little way up the back. But I could not feel or hear anything. I tried to look at my tongue. I stuck it out as far as ever it would go, and I shut one eye and tried to examine it with the other. I could only see the tip, and the only thing that I could gain from that was to feel more certain than before that I had scarlet fever. I had walked into the reading room a happy, healthy man. I crawled out a decrepit wreck. Our friend next visited a doctor, and there he got a prescription which said to eat well, to go for long walks, and not to worry his heads over things he didn't understand. See you in the next episode of Literary Snippets.